My name is Jonathan Tapson. I was for the last 3 years the Chief Science Officer of Grey Matter Labs, which is a startup trying to do neuromorphic chips. And so to some extent, my talk is going to be a little different than the prior ones. I'm reporting back, if you like, on trying to lessons learned from trying to build a neuromorphic architecture for commercial real-time computing. And throughout this, I guess the theme of this talk is what I call batch much less than one, which basically says that neuromorphic architectures are suitable for a particular kind of machine learning, and we should be focusing on that as an application rather than possibly claiming more general advantages. So I'm going to start with 4 slides from a fantastic paper by John Hennessy and David Patterson, who you may not know, but they are the gods of conventional computer architecture. Literally wrote the book. And they wrote a paper 2 years ago called A New Golden Age for Computer Architecture. And it started with 3 slides, which are kind of familiar to us. This one showing that Moore's Law is finally running out of steam. This one here, which pointed out that Dennard scaling, which has always said to us that as we go down in silicon process nodes, our power consumption does not go up per area. That no longer holds. There's Amdahl's law, which gave us a function for the extent to which multiple processes sped up and reduced computational time. That is also in a state of diminishing returns nowadays. And they put these together in this kind of pessimistic graph, which basically said we've taken all the advantage out of current silicon architectures that we can. And here we are in 2021. And we've run out of possible improvements from the conventional approach. But they came to a great conclusion. They said, this is a breathtaking opportunity. We'll have high-level domain-specific languages and architectures that will be fantastic, and we're going to see a Cambrian explosion of novel computer architectures, because as that general-purpose computing paradigm runs to an end, we have to get custom. And what I want to focus here is that they said domain-specific, and it was not accidental. It basically says any thought of a general-purpose computational framework is no longer particularly appropriate. And so the question for me is, we should be asking, or those of us interested in commercial or pragmatic neuromorphic computation, which neuromorphic architectures are suitable for which domains, rather than saying, here's neuromorphic and it's better than everything. We should be saying, for what is it better and why? So I first want to make a point about workloads. We're talking about domain specific in terms of what can we do. The top row here is 3 random pictures from the Caltech 101 benchmark data set, and it's an important data set. It's what many people have made their reputations on. And as you can see, they're completely uncorrelated. If you take 3 of them in order, there's no point in remembering what the last picture was, because there's absolutely no connection to the next. And this is a classic cloud workload. This is what Facebook has to process when they try to decide whether your picture is offensive or inoffensive. Is it a party, a sunset, a cat, or whatever? The bottom 3 frames show a typical edge workload, meaning something out on the periphery of the internet. It's a driving video, and obviously it's highly correlated. There's almost no change from frame to frame. And I guess one of the key arguments of this talk is the appropriate architecture for the top problem is an utterly different architecture to the bottom problem. So I'm making the point that edge workloads are different. They involve real time. You can't wait. In a self-driving car, you can't wait to accumulate a minute of information before you make it and batch it together before you make a decision. You have to take every frame as you get it. And they're continuous data streams. So whether they're video, audio, or EEG, it's a stream rather than a series of unrelated events. And we can exploit that. We should be exploiting that. Another important characteristic of these edge data streams is there's a lot of data coming at you, but there's very little information. And if I give you the example of a smart speaker, even if they only have 2 microphones and some of them have as many as 6 or 7, they're sampling at 16 kilosamples per second. you're getting half a meg or a megabit per second of data, but you're listening to human speech, and human speech universally across every language and pretty much every circumstance averages about 39, 40 bits per second. So the dimensional reduction from data to information is enormous. And similarly, for a smart doorbell, it's even worse. These things are on full-time 79 megabits per second of megabytes per second of video coming at you. And if there's no one standing in front of your door or nothing happening in front of your door, there's no information. The informational content is zero. So we're thinking about ways to close that gap or exploit that gap in a useful kind of a way. And here's an example. This is a picture taken from my front door. It appears to be a lot of information in this picture. But if you look at the difference between any two frames, here's the difference between that and the next frame. And there's actually a lot going on here. It's not just the cyclist. If you look carefully, you can see ghosting of a lot of stuff happening in the background. But fundamentally, there's not a lot of new information in each frame, and we need to understand how to kind of get that out. However, something that I think we fool ourselves around about in the neuromorphic community, if you like, is that in order to remember what's going on and exploit that, we have to maintain state in our system, and it's expensive. So across the top here, I'm not sure if you can see my cursor. Can you see my cursor? Great, thanks. This would be a conventional CNN. Get a frame, throw it into a convolutional neural network, and you're done. This kind of diagonal path going down is what happens when you, sorry, I'm just checking out my time here. That diagonal path is what happens when you are trying to maintain state. And the problem is not only are you remembering what the last frame had, and calculating a delta, a difference, you have a lot of process going on. At each point through the network, you have to perform a delta update. And so even if you're using, for example, the DVS camera, sure, that gives you the initial deltas for nothing, but the rest of the network has to perform that function. And this is very, very costly in terms of memory. Okay, so in order to actually make that pay, we have to exploit sparsity, and there's multiple different kinds of sparsity we can exploit. There's sparsity in space, time, connectivity, activation. And I'm not going to go into that too much because I want to keep moving along. But basically, each one of these situations allows us to say, stuff is not really changing, or stuff that is changing is not important. Let's not compute it. And we have an opportunity to exploit all of that in a neuromorphic architecture. So how do we exploit that? What are the advantages of a neuromorphic computing approach? And I mean, you're all, if you're in the community, you're probably sick to death of this, but we have spikes and events and sparsity, asynchrony. We can use analog signals, as we've seen these two very good presentations. We can use stochasticity, we compute in the network, and we have, again, as we've seen in recent presentations, multi-scale connectivity. However, not all of these can be applied at the same time with the same amount of usefulness. And if I give you an example, think about coding of numerical input. Okay, biology uses spikes, it doesn't use numerical variables at all. Machine learning requires numerical variables, and they are not actually robust necessarily to loss of precision. So if we want to use numbers in a neuromorphic system, we have to encode, and we either encode with spikes or we do something else. And encoding with spikes is, again, not simple. We use time coding, rate coding, population coding, ensemble coding, each of which is a choice that has certain penalties, advantages, and penalties. One point I do want to make to you is that however you code, and here we show spike binary coding in a number of different, serial, parallel, population, and ensemble ways. It's actually very much the same number of transitions, with the exception of ensemble coding. But there's a lot of digital transitions happening, whether we use spikes or conventional bit encoding. We don't actually have an efficiency gain. And what I've superimposed here is a picture of a classic packet, such as we are all using. We all have digital packet switch networks these days. And so here's a packet from a typical network, and you look and you see that it's a 40-bit packet, and the data payload is the stuff over here on the right. In this case, it's actually passing 8 and 16-bit values. But the point being, even if it was just one spike, I still had to send the whole damn 40-bit packet to make things happen. So our kind of mental conception of these beautiful, neat, and elegant spikes is kind of belied by the fact that to communicate them, we're actually packet switching 40-bit packets, or 41 or 42. So these are choices which are made in this process. So I'm going to present you an architecture. It's digital. It doesn't encode values as spikes because a decision was made to encode values as numbers, and you actually still get a tremendous amount of the value of neuromorphic computing, sending numbers around your system. So it uses events. The numbers are events. It exploits sparsity in every one of the possible ways which I have outlined. And it has the benefits of computing network and multi-scale connectivity. And what do we give away? It's not asynchronous because, as I'm sure Mike Davies would be the first to tell us, that's not simple. It doesn't use analog, and it's not stochastic. And those are losses, but these are decisions made to achieve a particular goal. So the particular architecture that I want to present you, just as one method of doing this, is from Grey Matter Labs. It's called Neuroflow. It's particularly designed, as we all design these days, for machine learning inference, although it can also do DSP and procedural computation. And the emphasis is on getting low latency and high efficiency by processing only changing signals in real time. So only that which changes is processed as it changes. It's called Neuroflow because it's a hybrid of neuromorphic computation and data flow. Data flow is a computing paradigm that was kind of fringe since the 1970s, and is now coming back into vogue, if I can put it that way, because it was a way of modeling and designing multiprocessor architectures from the point of view of the flow of data through them rather than the processes that they implement. And it has a lot of commonality with neuromorphic engineering. Plus, it has a good formal architectural design methodology. So data flow models processes as actors, and neuromorphic engineering models processes as neurons, but intrinsically they're actually not unsimilar. They're reactive in the sense that they don't do anything if they don't get data, and they focus on that sparsity of activity. So we're able to hybridize them. So what is Neuroflow? It's a network of neuron clusters. They're connected by a packet switch network on chip. They process 8, 16, or 32-bit data, so it's digital. Everything, numbers are numbers. But all processing is event-triggered, so nothing is scheduled. But data is not pulled. Just as a number gets to a neuron, it's processed, and if its processing results in an event is generated. So we have actually instantiated this in silicon. We got our first chip late of 2019. Obviously, we're now a year later, having had a year delay on this conference. It was a 196 core chip, and you can see here, I think, is the most interesting thing. The dark gray is processing, the light gray is memory, and so every single neuron is closely embedded in its particular memories, which are there obviously to reduce power usage, and so you can instantiate 200,000 neurons with this chip, which was very much just a proof of concept. So what happens inside one of these neurons? So events arrive, as I say, they're not pulled, they are pushed. So events will arrive in a neuron, having been routed there by their generating neuron. They get queued as a set of events. Locally, they get multiplied by weights, and then the multiplied weight is applied to the particular neuron to which it was being sent. So in each processor, there's typically 1,000 neurons. And then if that neuron generates an event, it goes out via a synapse table and gets routed out to its destination neuron. So again, no great surprise, I think, to many of you who've been seeing many of the architectures in this field. And just a general top-level view of the chip. And so standard GPIO interfaces, JTAG, and the usual JTAG monitoring interfaces coming in through routers and then being networked onto the clusters, the fabric of 200 clusters. So we applied this architecture to some very straightforward machine learning tasks, rather simply because this is the currency of our industry at this stage. So here's a self-driving car network for a data set called PilotNet, which is from NVIDIA. And the keys here are, it's got incredibly low latency because you're basically processing one layer per clock cycle. Data is getting through this network in 20 microseconds at a dynamic power of 10 milliwatts. So full frame, zero batching, low latency processing at 10 milliwatt continuous power. And some other results, we've used it for some of the standard keyboard spotting and gesture recognition, the kind of standard data sets, and again, typically incredibly low latency, which is not so important for, I guess, keyword spotting, and extremely low power for these recognition tasks. So I guess this is just proof of concept that this kind of architecture can do a formal machine learning task and can save a great deal of power, notwithstanding that it's not batch processing these images. And the cool thing being a neuromorphic chip is that you come out with a kind of energy space. You can run it slower if you want to run some low processing task like keyword spotting. You can run it faster if you're processing video. So by running at different frequencies and different voltages, you wind up with a kind of window of potential power that from 25 milliwatts up to over a watt, depending on the task that you want to perform. And again, going with the commercial paradigm, we came up with a very good SDK approach to this, where from the application layer, you came down through typical industry interfaces or applications like TensorFlow or just straightforward Python. We have, since the slide was made, dropped C++ support simply because almost nobody requires that, but it drops down through, and then you have a critical feature, which is a mapper. And I guess the reason for presenting this slide is just to say, we as a community, we tend to be very hardware focused or maybe algorithm focused, but actually how you get your algorithms onto the hardware is the stumbling block of almost every single one of our projects, whether they be academic or commercial. And more than half of the effort that was put into Greyflow was put into the software stack, simply because nobody's going to use your stack unless you use your hardware unless they have some fairly easy way into it. And I make an exception for that. There are a lot of people in this community who've put in the hard yards to program some of the excellent platforms that we have had. But if you want to get real world, massive bodies of users involved in these things, then there has to be a very easy introduction, a very slow learning curve. A very shallow learning curve, if I can put it that way. And so this is it. You can write, for this chip, you can write an algorithm in TensorFlow. There's a mapper that operates behind the curtain to decide how it runs on the various processes, and you can then either simulate it or actually generate code that runs on the chip and actually get a result. And if you want to, you can do kind of the classic drag and drop, click to connect programming and simulation. And so here's a simulation of an RNN model, which was simulated on Jupyter Notebook and then generated as a block diagram with recurrent connections. So I think that pretty much says it all. I may have ripped through it a little fast, but that leaves us a good time for questions. What I want to say in conclusion, I guess my message is, yes, there is going to be a Cambrian explosion in computer architectures. However, the key to that explosion is that they're going to be domain specific. And if we can't say for which domains our architectures are suited and why, then they're not going to fly, are not going to be adopted. And in that spirit, I believe that neuromorphic architectures are particularly well suited to workloads in which the data is real time. The data streams are highly correlated. they're sparse, and therefore we can use batch much less than one processing, meaning that per frame, we do less than one frame's worth of processing. If we can achieve that, then, and neuromorphic architectures are extremely well designed for this, then we can take part in this golden age. And I presented to you one particular neuromorphic architecture which takes some of the principles of neuromorphic engineering, very specifically selected to achieve a particular result, and hopefully therefore optimizes for one outcome from this process. Thank you very much.